Good morning. So we will see how to generate a square waveform using or by creating delay. Okay. So this delay we are going to see generating a square waveform only by using instructions that creates delay, not by using timer. Okay. So let us take the crystal oscillator frequency XTAL to be, let it be 30 megahertz. Okay. Let it be 30 megahertz. So how you will be calculating your machine cycle? For example, one clock cycle will be equal to in 8051 microcontroller. One clock cycle will be equal to, or 12 clock cycles will be equal to one machine cycle. Okay, so 12 clock cycles will be equal to one machine cycle. Will be equal to one machine cycle. So if we are having, okay, if we are having the 30 megahertz crystal, 30 megahertz crystal instead of the normal crystal that we are having in the lab, which is nothing but 11.0592, which is nothing but 11.0592. Okay. So how will you find your machine cycle operation? So you can do it by, so that can be done. You divide by the 30 megahertz frequency divided by your 12 cycles, and if you take the inverse of it, you will be the time period for one machine cycle. Time period for one machine cycle. Okay. That is how we will be finding out your machine cycle value. Keep in mind, we are not using timer. We have not yet used timer, and we have not dealt with timer so far. Okay. So the time required for one machine cycle, let me calculate. It is 30 divided by 12. Okay, it's 2.5. And if I inverse it, it is 0.4. So this is 0.4 microseconds. Okay. This is 0.4 microseconds. So now we need to generate a square waveform. Let me generate a square waveform for, okay, let us generate a square waveform for 3 seconds, or generate a square waveform for this one. Let me take, let it be 3 kilohertz, right? So meaning with 50% duty cycle. With 50% duty cycle, let us generate a square waveform. So your turn on and the turn off time will be even, meaning equal. T on will be equal to T off. Okay. So such that your total time period should be 1 divided by 3000 whole inverse. So 1 divided by 3000 inverse of it, 3 into 1 divided by 3000. So it is around 0.33 milliseconds. So the total time period is nothing but 0.33 milliseconds. Okay. So we need to generate 0.33, the delay should be like that, 0.33 divided by 2. You should create a delay of 0.33 divided by, okay, 0.33 divided by 2. Here you will be using your control transfer instructions. The question is you need to generate this delay or the square waveform, okay, to generate the square waveform and in port P1.0. In port P1 dot, okay, in port P1.0. Let me use in instructions either let me move. I need to calculate the count. Because before that, let me finalize what all the instructions you can use it. Okay. So let me load some count value. Let me load some count value. Move. I will be using a register R2 as my counter. Okay. And loading an immediate count value. Let me name it as N for time being. Okay. And then decrement this count. Decrement jump on non-zero. Okay. Which value I'm going to decrement the counter value. Till it is non-zero, I'll be decrementing by 1. If it is not 0, it has to again and again it has to go to the decrementing part. It has to go to the decrementing part. So this is how I'll be using this instruction, subroutine or the delay. Okay, subroutine or the delay. So I need to load some value. I'll be decrementing this R2 register till I'm getting 0. Until and unless I'm getting 0, I'll be looping it itself. I'll be looping the delay. Okay. Calculate the delay. So now we know the move instructions will be having one machine cycle, whereas decrement jump or non-zero will be having two machine cycles. Okay, two. And if we are using this delay in a subroutine, the return instruction will also carry two machine cycles. Okay. So 1 plus 2n, okay, into how many machine cycles? One machine cycle is equal to around 0.4 microseconds. This 0.4 microseconds should be equal to this 0.33 milliseconds. But this is a calculation because we need to create a delay of 0.3 milliseconds. We need to create a delay of 0.33 milliseconds provided the on time should be 0.33 by 2 and off time should be 0.33 by 2, and we need to generate this in the port P1.0. Alternatively, the P1.0, the bit P1.0 to bit should be 1 and 0. So you need to complement the bit 1 and 0 alternatively. We will be complementing the bit 1 and 0 alternatively. Since we have taken the XTL frequency or the crystal oscillator frequency to be 30 megahertz here, 30 megahertz here, one machine cycle is equal to 0.4 microseconds. Okay, 0.4 microseconds, and we need to create a delay of 0.3 milliseconds by 2. 0.3 milliseconds by 2. So if I'm using a nested loop, okay, nested loop in the sense, if this n value, for suppose if my n value is greater than 255, we know each and every register can store up to a decimal value of 255 only, because 8 bit 2 power 8 it is 256. So 0 to 5, so that's 5 So this is 0.4 into 0.4 into 2. That is the point. So 0.8 microseconds into 1 plus 2n will be equal to 0.33 milliseconds. Okay. So again 0.8 milliseconds plus will be equal to 0.3. Okay. So then I need, we will take like milliseconds. That is fine. So 0.33 divided by 0.8 divided by 10 power minus 3. Okay, this value divided by 2. L value is around 205.75. To the question, in the manual, we need to use port P1.0, the bit, 0th bit in port P1.0. So here, what I'm going to use it here is, so I need to complement this bit 1 and 0. Alternatively, I need to complement this bit 1 and 0. So now what should I do? Let me use bit manipulation instructions. So complement, okay, P1.0. Okay, this we have to do once when the delay is over, I have to come here and complement the bit. And again, I have to go back to the delay calculation and I need to complement the bit. Okay, again and again, I have to go ahead with that. Okay, then complement, after complementing, okay, what I should do? I should call the delay. So let me use an absolute call, a call delay. Okay. So in the delay subroutine, okay, in the delay subroutine, what I'll be having, let me move the count first, move R2 comma hash, now it is 206 decimal, okay, and then decrement jump on non-zero, okay, your R2 register, till your R2 register is 0, I need to jump here only, okay, I'll be jumping here only, okay, so it's normal jump, an 8-bit jump, 8-bit jump, short jump, otherwise said to be a short jump. And then what I have to do? I have to return to the main program. After doing this delay, after creating this delay, I have to return to the main program where I left with. After calling the delay. So return statement, I hope you remember this. Whenever the call instruction is executed, the PC value at that time before execution, the PC value will point out this instruction, the next instruction in sequence. So that address, whenever after execution of this call, the PC value will be loaded in the stack, okay, and then it will go ahead with this delay. Delay is nothing but again an 8-bit address. So PC value will be having the delay address. Let me write it as delay itself here, and then it will jump to the delay. And whenever you have an return instruction that is being executed, automatically your PC will retrieve the data from the stack, and then it will go to the next instruction in sequence in the main program. Okay. So where you need to go after delay, I need to complement the bit. Okay, I need to complement the bit. Let me use an unconditional jump, S jump, short jump. Okay, short jump, and let me do it as square or again, whatever. Okay, I need to go ahead with this square. Okay, so this is how the statement is. The program ends here. Okay, once that is done, you can have an end statement. You can have an end statement, and you can use even your assembler directive org. Start your program from here, from this address. Okay, so let me use org. Either I can instead of going ahead with this, let's jump again and again. I'll be using org 2000h. Let me use this address for storing the program. So from where I'm instructing the compiler that store the program or the instructions that is followed in the program, namely CTL and so on and on. Start storing it from address 2000H. Okay, this is what I'm instructing the compiler. So this is the program. Now do this and check your on time and off time. And how will you do this? Please type down your code in your key microcontroller software.
Okay guys, I have typed here the delay program using port P0.2. Okay, we have calculated the count value to be 206 decimal. So see here, complement P0.2, A call delay, S jump again, move R1 hash 206, decrement jump on non-zero, R1 comma here, return and the end. Okay, this program I have typed it as for the 30 megahertz is the crystal frequency. So project select options for target. In here you type 30 megahertz because we are going to use 30 megahertz crystal here. Press OK. Okay. After that, just run. Build your code and then debug. Okay. And then run. After this, okay. After this, you go for the analysis window. You go ahead with logic analyzer. Okay. Logic analyzer. Yeah. See here, actually, you have a pop-up window called Logic Analyzer. In that, go ahead with Setup. Here, already I have typed and kept. Now, what is in which port you are going to see? It is P0.2. So for me, so let me type it and then I will take it. Okay. Already I have typed it P0.2. Display type is bit and the color I have given it as green now. So let me change the color. I can give it in orange and then close. Okay. So the previous one, both are giving the same input, the same output. Provided this is your, I have given two different colors. That's all. Okay. And so this is how you will be getting your output waveform. This is how you will be verifying your output waveform with um, your logic analyzer window. Okay. Since the count value is 255, since the count value is 255, what we have done, we have used only one register, namely R1. If we need to use nested loop, for example, if your count value is more than 255, we will be using nested loop. With the same count value, I'll just tell you how to use nested loop. Okay, take the square root of this 206. Okay, take the square root of this 206. So that will be getting 15 and 14 now. If you take around 14.5 or something like that. So let me remove this. Remove file. Already I have from the source group, I will add files into the source group. I am searching for the ASM file and then I'll go for del.asm. With the nested loop, the program is there. So del.asm is this. See, we have used two registers here, R0 and R1. So I'll be using 14 and 15, 206 decimal approximately. I'll be taking 14 and 15 as the count. I took the square root and decrement jump on non-zero R1 come here. Decrement jump on non-zero R0 come go to here. Okay, the outer loop return and end. That is the only difference here. So again build your circuit, debug. I'm sorry, I forgot to check the project whether it is a 30 megahertz crystal or what. 1. Okay, delete this, close. Okay, and in the new keel, this is the older version of keel. So here you can even have trays and all here. Okay, so I can verify for your output. Hmm. So, and then I will go ahead here and we can check. Okay, yeah. With this, I'll stop today. And in the new keel, you can go ahead with even your frequency range calculations. That will be given as delta. You have a trace window. You can even stop this. It's continuously moving. You can stop and you can